Solution of the harmonic oscillator 1. Find the integral equation for x that is equivalent to the differential equation. This is an equation of motion for the simple harmonic oscillator. The general form is a double time derivative k over m, x equals to 0, and we know this is a positive definite because the spring constant is positive and mass of the particle is positive, and we usually use the frequency, angular frequency, square root of k over m. Then it becomes omega 0 squared. Therefore, we have divided both sides with omega 0. So omega 0 squared x double dot plus x equals 0. This is style. Because this is omega 0 t is a differential squared d squared x style. So this one, omega 0 t is tau, and t has a dimension of time, and omega 0 has the dimension of 1 over time to make the tau that is independent of any physical dimensions. Still, we have x that has physical dimensions, then that can always be scaled out by factoring out the scaling factor that is called amplitude. And remaining piece, actually we know the answer is exponential tau, exponential minus I tau, and actually omega 0 t, or cosine tau, sine tau, that is actually cosine omega 0 t and the sine omega 0 t. So, okay. Consider this equation. This is called the differential equation. This is called the second order differential equation because we have a double derivative that is a maximum application of derivative operator. So second order derivative. So there will be two, and this is a homogeneous equation because it equals to 0. And we have the first order term disappears. So it is a very simple. That disappearance can be made by factoring out some exponential factor that is finally equivalent to completing the square of the quadratic expression. So we can always remove this part by translation coming from the factorization of the answer. Okay, in that case, our equation becomes a very simple equation. Okay. We'd like to solve this equation by integration. So we don't have to learn differential equation class. So if we take the integral both sides, what happens? If I do the integral over what? This is a double integral, double derivative of x. So what we carry out, this integral is integral over this guy. Okay. However, if we attach the differential, then that is integrated out just like the sum over k. This sum, this summation index is a dummy. It disappears at the end of the day. but the upper bound, lower bound, and the upper limit, lower limit, they survive just like a and b in the integral. So these are equivalent. They survive. However, this one is something like k, and we would like to express this one as a dummy variable. So this one is tau prime, and tau prime. So we would like to pull the integrate out outermost derivative. And if we make use of lower limit, explicit lower limit, and explicit upper limit, then the identity is still valid. There is no ambiguity like indefinite integral. So it is definite integral is equation, the same identity holds, but you have to keep exactly the same lower limit and upper limit. If you sum all of them, the summation should be made equally, consistently. So if you carry out the integration over the tau, the right-hand side should be integrated with the same measure. Okay, and even though I wrote nothing after x, it is actually function of tau. And during the integration, I would like to replace this time with the dummy variable that is integrated out. Only the time dependence, this tau dependence, appears in either lower limit or upper limit. But for simplicity, I fixed the lower limit 0 and upper limit of usual variable of scaleless time, that is tau. After integration, I have the integral, but left-hand side, this integral is trivially obtained because it is expressed as a derivative. If you know the derivative, then integral is the primitive function. So if I remove one derivative, then your primitive function is the first order derivative. So it is the left-hand side is completely determined by the lower order derivative. Evaluated at the upper limit, subtracted by the value at the lower limit. Because we do not know the exact value functional form of x, I will leave it as it is. It is just the integral. Only if you know the form of this function, you can evaluate this integral. However, left-hand side, you don't worry. You are given as a higher order derivative, and just the one order lower derivative is the indefinite integral. So that's fine. It's completely determined. Okay. And then still we are left with the single derivative. Why don't we integrate out over the same period, same time interval? Then this integral should be evaluated. At the right-hand side, we have a double integral. First integral, and then now this one is integrated out, but I'd like to integrate over the tau prime. So let me write it as a double prime inside and put it as a prime. In that case, in here, this one has been replaced with this double variable. And then this upper limit is identical to the differential of this integral. And then finally, after you integration, your final upper limit is to be replaced with the tau. So these tau double prime and tau prime are all dummy variable of the first integral and the second integral. The reason why I attach the tau just right after the integral sign symbol is that without this, I need to write it in this kind of complicated way. The tau prime, 0 tau, 0 tau prime, d tau double prime, x tau double prime. It's too busy. So it is convenient to attach this one right after the sign of integral. So you should be careful about this notation. If you have multiple integrals, it is convenient to write in this kind of form. Okay, we again carry out the integration of the left-hand side. That can be done completely. First of all, this part, this guy, this is first order derivative, so its indefinite integral is just x itself. So evaluate it at the upper limit subtracted by the lower limit. Okay. And then this guy, you have substituted tau prime with the 0. So this is an actually constant. It's nothing but a constant. So what's that? This is dx dt prime at t prime equals 0. So initial velocity. Sure, it is not exactly the same as velocity because tau is not time. It is a omega 0 t. And we have in here this initial position. So we have two parameters, the two integration parameters. And corresponding to those parameters, we have a function, identity function, and we have tau, linear function. Two linearly independent functions are multiplied by these two parameters. They are called the integration constants. And then your final result depends on this. So this is the integral equation. Let me see if it is true. You can take the derivative twice, then it is constant. It is a linear function. This one disappears. We need to see whether this integral satisfies the original differential equation of motion. Okay, we make use of the identity, derivative, x, then the result is your integrand. So using that method, you can take the derivative, the constant disappears. It used to be a tau, the simple velocity, only the coefficient survives. You take the derivative with respect to this, so you just erase and you are left with the single integral. And then you take another derivative. Because it is constant, this guy disappears, and this tau the same. What you get is the integrand with the negative sign. Okay, you are end up with the same differential equation. So my solution is exact solution. And if you substitute this guy, this one will disappear in the equation of motion after the second order derivative. So the solution can be obtained. We find the general solution for this. Show that this is a linear combination of a cosine and sine. Another simple way is that you know how to take the derivative of sine, cosine. Using this, you can carry out integration as it is. The double integration is also possible. So finally, using these results, you can evaluate the double integral of this, that is this. Okay, you take the second order derivative of this function, and you will find this one disappear after the second order derivative. And this function, you know how to evaluate the double derivative. It is identical to itself except that we have negative sign on it. Finally, you have found that this satisfies the equation. So because what you have in C1 and C2 completely correlated, this one. And actually, even though after the second order derivative, this guy disappears, still the free parameter dependent solution, you have two linearly independent solutions survives. That's the reason why the linear combination of cosine and sine is a complete set, constructs a complete set of general solution. So this is a kind of tricky way in comparison with what you learn in the standard differential equation, but logically there is nothing wrong. So this is a kind of physicist way to derive the mathematical derivation, but it is exact. It's not a fake.